Welcome back to chapter 26. We're going to look at color and some optical instruments. So color and color vision. So the color receptors in the eye are called cones, and we have three different kinds, red, blue, and green. These correspond to the primary colors of visible light. This is not like crayons or paint. With crayons and paint, that is reflected color. So you have an opaque surface and light hits it and bounces off. With visible light, we're talking about the transmission of light. So if we have red and blue and green light, it makes white light. If you have red and blue light, you end up with magenta, which is kind of a hot pink color. If you have red and green, you get yellow. And then if you have blue and green, we have cyan, which is kind of a turquoisey color. These three, magenta, yellow, and cyan, are referred to as the secondary colors of light. So red, blue, and green are the primary colors. Magenta, yellow, and cyan are the secondary colors. If we look at our little colors, so we've got green light, red light, and blue light combining to make white light. Green and red will make yellow, red and blue will make magenta, and green and blue make this cyan color. So again, this is for visible light, transmitted light. This is additive mixing. Subtractive mixing is paints and inks. And you might think back to the boxes when you buy ink for a color printer. You'll notice that it's magenta, yellow, and cyan that you're purchasing, and black, and that we get these other colors by combinations of them. So let's look at what a filter does. A filter can only pass a color that it's composed of. So a red filter only passes red light and it will absorb blue and green. A green filter only passes green light and absorbs red and blue, and so on. Filters that are made out of things like yellow, for example, a yellow filter will pass red and green light and it will absorb blue light. A cyan filter will pass blue and green light and absorb red light, and so on. So if you had a yellow filter and you were shining a blue light source, because the yellow filter doesn't pass blue light, it absorbs it, the result would be no light would come through and it would look black. If you had a cyan filter, which lets blue and green light come through, and your light source is blue, then you would see the blue light. If you had a cyan filter, and remember that lets blue and green light come through, and you had a magenta light source, magenta is made up of red and blue, the red would be absorbed by the filter and the blue would pass through. So let's look at some of this subtractive mixing. We'll do some of this color mixing in lab. So subtractive mixing, opaque surfaces reflect light. So a surface will reflect some light and absorb some. If you have magenta, cyan, and yellow pigment, you end up with black pigment. If you have magenta and yellow, well, magenta will absorb any green light that hits it and reflect red and blue. Yellow will absorb any blue light that hits it and reflect red and green. The color the two pigments have in common is red. So if you mix magenta pigment and yellow pigment, you end up with red. If you have magenta pigment that'll absorb green and reflect red and blue, and you have a cyan pigment that absorbs red and reflects green and blue, the color they have in common for reflection is blue. So the blue gets reflected both by the magenta and the cyan. That means it would look blue as the light bounced off. If you have yellow pigment, it will absorb any blue light that hits it and reflect only the red and green portions. If you have cyan pigment, it'll absorb any red light that hits it and reflect only the blue and green. The color they have in common is green. That's the color that comes through, that bounces off. The three secondary colors for pigment are red, blue, and green. Those three secondary colors are red, blue, and green. So primaries in pigment become secondaries in visible light and vice versa. So if you have a yellow object, it'll absorb all the blue light that hits it and reflect any red and green that hits it. And you shine a blue light on it, what's it going to look like? Well, the blue light's going to be absorbed by the object. And so your end result is going to be that it will look blue. It's going to look blue in, oh, I'm sorry, my mistake. It's going to look black. If you have a yellow object under blue light, it'll look black. If you have a cyan object that absorbs red and reflects blue and green, and you shine blue light on it, it will look blue. If you have a cyan object that absorbs red and reflects blue and green, and you shine a magenta light on it, well, magenta is made up of red and blue light. And so the red part gets absorbed, but the blue gets reflected. And so what will happen is your cyan object is going to look blue if you shine magenta light on it. Let's talk just a little bit about microscopes. So microscopes enlarge the details that we can't see. They've been around for a really long time, since the early 1600s. The most common is an optical microscope. It uses light that bounces off the object and then passes through a series of lenses to enlarge the details. There are other kinds of microscopes. You can have an electron microscope, different types of electron microscopes. You can have an ultra microscope and scanning probe microscopes, and even fluorescence microscopes. What's really cool about this is these different types of microscopes all let us see smaller and smaller objects, finer and finer detail. And it all has to do with the wavelength of whatever electromagnetic radiation you're shining on the object and then allowing to bounce off. Whoops, I overshot, I apologize. So the simplest type of optical microscope is your compound microscope. You've got an image formed by the first lens. So you have the object, and then the first lens forms the image that becomes the object for the second lens, and you're then able to fine tune it using your eyepiece, which is called the ocular. Typically, these magnifications go anywhere from 5 times to 100 times. You've all used these kinds of microscopes in biology class, I'm sure, at some point in time. And we have a little graphic that shows what's going on. So here's your object, a little object. This lens makes it an image, and this image becomes the object for the eyepiece, and then you end up with an even larger image along the way. You'll notice in this kind of simple diagram, what we end up with is that it's an inverted image. And some of you may have noticed that on your microscopes. Well, we take, as I said earlier, different kinds of microscopes to let us look at smaller and smaller objects. The smaller the object, the smaller the wavelength of light necessary to view it. So visible light has a limit. So instead of thinking of it as just in terms of light, you might want to think of it in terms of electromagnetic radiation. So we use things you cannot see to bounce off these images and then these objects, and then process it to give us better magnification. Let's talk briefly about telescopes. There are 3 kinds we're going to mention: refractor, reflector, and radio. So a refractor telescope, sometimes called a Galilean, uses a series of lenses to help you look at a distant object. So if you're looking at a distant object, the light comes in from the distance, gives you a first image, a second image, and then a final image. So our object is way out here someplace. Remember, telescopes to look at things really far away. But the refractor just uses a series of lenses. The reflector telescope, sometimes called the Newtonian or the Cassegrain, uses lenses and a mirror, which is where the term reflector comes from. It uses a mirror, and you can see that it takes light from the distance. So your object is way out in space somewhere. The light comes in, hits the curved mirror, hits another mirror, hits a lens, and then you see the image. This allows you, this mirror system allows you to collect more light than you would normally be able to collect if you just used images. So it's more popular when you're trying to view things that might be very faint. And then the last kind are radio telescopes. Radio telescopes don't look at visible light at all. Instead, they use antennas to search for radio signals from deep space. We know that parts of our universe emit radio signals, and so we can look at those with our radio telescope. The signal is brought in and amplified, and then it's processed with a computer, and it turns those radio signals into an image which we assign colors to. So we assign false colors to indicate the intensity of the radio emission at different locations. So we can look at cool clouds of hydrogen in space that are out there behind the stars. Hydrogen atoms are the most common forms of atoms in the universe. And so much of the hydrogen gas is too far away from any star to give us an emission in the optical band. That's why we end up looking for the radio signals. Radio telescopes have to be really big. The largest ones are enormous. In fact, the largest fully steerable radio telescope in the world is located in West Virginia at the Green Bank Observatory. So we will stop with this. We'll stop the share. We'll stop the recording.